Okay, so when we deal with digital images, as opposed to images represented as a function of a continuous space, we are performing uh, actually two processes. The first is that we're dividing up continuous space into a series of grid elements. So that's a process of regular spatial sampling of the two-dimensional spatial function f as a function of x and y onto uh, a discrete representation f as a function of m and n, where it's usually understood that m and n are integer variables. Okay, so they can generally take values that are positive or negative or zero, but integer values. So -1, -2, -3, +1, +2, +3, and so on. And so the a digital image f, as a function of m and n, can then be thought of as a mapping from the space z squared, so integer values of m and n, onto the set 0 and positive real numbers. So the second process that's involved in creating a digital image is not one that we usually think about very much unless we're thinking about image compression, which is a particular topic or field of image processing. Um, so the point here is that the representation of the intensity as well of f. So we no longer think of f as taking any possible positive real value or zero. Instead, we have some sort of finite precision in the way that we can specify this real number here. So for example, if our intensity ranges from 0 to 1, we may only have a finite number of steps in that range, which can be used to represent intensity. Now, the reason for that boils down to the precision with which we can measure, uh, well, two things actually. It's first the precision with which we can measure intensity in a practical camera sensor, and the second thing has to do with the hardware requirements that limit how we can display images on screen, but also to some extent which limit how many discrete values or how many possible intensities we might consider as being useful to capture and represent within our computer. Okay, so um, let's now have a look at what this discrete image f as a function of m and n might look like. So here's an example fmn, and in this case we have two spatial coordinates m and n which rove over the grid. Um, so f is a function of m and n, and m represents row coordinates, so coordinates of row location into this two-dimensional array, and n represents the column coordinates. Uh, and so in this particular case, we've got 6 rows in this image, so we sometimes write large M is equal to 6, so I'll often refer to little m as being a row number and a large M as being the number of rows. And so we can say little m takes values 0, 1, 2, up to 5. And more generally speaking, if we didn't have simply 6, but we wanted to generalize this to m number of rows, then little m takes values 0, 1, 2, up to large M minus 1. And you have a similar range of values for n, n equals 0, 1, 2, etc., up to large M minus 1. Now, in this case, we're looking at a finite sized image, and most of the images we will deal with in image processing will be finite in size. And that, of course, boils down to the number of pixels we can capture. So putting a sensible hard limit on this, but allowing that hard limit to be variable um, is something we commonly do. So large M and large N represent the size of an image, generally speaking, within these lecture notes. Okay, whoops, It's scrolling a little bit too much there. Okay, so let's go back to uh, our notes. So we normally assume that the in moving from a continuous intensity field to a discrete intensity field, we do have some theoretical considerations that come into play, but we often ignore them. Um, but if you have done a course on signal processing, you will know that there is something known as the sampling theorem or the Nyquist-Shannon sampling theorem, which which sets um, a limit on the minimum rate of sampling that we need to use to capture a time varying signal to sufficient quality that we can reconstruct the continuous signal from it. So these considerations are also applicable in moving from a continuous intensity field to a discrete image or discrete intensity field. But we often ignore them. But the place that they happen in something like a mobile phone camera is that there is actually a little bit of there's a little bit of blurring or low pass spatial filtering that goes on within the imaging system or the optics of the camera. Um, uh, Digital SLR cameras also have these anti-aliasing filters that are placed in front of the CCD chip. So it's not something we'll go into in more detail in this lecture, but you should be aware of these things. So I talked about the fact that we have a finite quantization on the real value of intensity, and that is very much the case for digital images. So when we store a digital image on the computer, we're storing a value at each of the locations that we've described on our two-dimensional grid. So we have our image array, but within that image array, we can only represent the intensities with a certain number of bits. And that certain number of bits limits the precision with which we can describe intensity. So there is this quantization thing that goes on in the description of an image. And often what we tend to do is to use, if we're talking about monochromatic images or rather grayscale images, we often use 256 levels of gray if we're talking about images acquired with a standard camera on, say, a mobile phone. In medical imaging, there are some cases where we have the capability of having a large number of shades of gray, but it is very difficult to represent that very large number of shades of gray on a standard computer monitor, such as that of a laptop or a PC. Um, but if we do have 256 levels of gray, then what it means is that we can represent the um, the intensity at each pixel by a single byte of information, and that's quite a common representation for monochromatic or achromatic digital images. So in other words, that two-dimensional array that I showed you earlier would effectively consist of a two-dimensional array of bytes which capture the intensity information within an image. In the case that we want to represent color images, there are lots of different ways that we could proceed. So first of all, we could use a triplet of bytes to represent each pixel. So if we think of our color space as being restricted to the RGB color cube that we talked about, that we introduced earlier on, then the use of one byte for each of red, green, and blue is probably the most natural way we have of representing a color digital image. However, when storage space is scarce, what we might resort to doing is using a combination of a color map and a single byte per pixel. And that needs a little bit of explanation, so I'll come on to that in a second. But in such a case, we can represent a color image uh, by using each byte to represent not an intensity for each pixel, but rather an index into a lookup table where the color values are stored with full RGB components, possibly to greater than 8-bit precision, but usually also to 8-bit or 1 byte precision. So this needs a little bit of an explanation, and you're going to be doing a practical on this, so hopefully things will become quite clear through the practical. But let's just talk about this particular notion of a color map representation now. So um, if I decide that I want to use a color map representation, what I'm essentially saying is that I can do the following. So even though it's pretty obvious that I can use one value at each of my pixels to represent an intensity, I can the if I take this color map idea, then I get some more flexibility. So let me just illustrate that. So first of all, here's a simple and small digital image. And what we do is we have one value at each of these spatial locations. And here is a color map and what the color map structure looks like. So what I do, or what I have, is um, is 4 columns in this color map. Uh, there we go. That's 4 columns. So the first of these is going to be it's actually an index value. So let's call it I for the time being. The second of these columns is going to contain the red, or the intensity we want on the red channel. The second column is going to be the intensity we wish to specify on the green channel. And the third is going to be the intensity we wish to specify on the blue channel. So the color map is kind of like a paint by numbers sort of thing. So if you've ever done paint by numbers, you'll know that what you do is you've got you basically buy or find these paint by numbers things online. So what you have is a tracing of a drawing containing um, different regions of where within the drawing where you've got a number, and that number tells you what color of paint you should you should sort of paint into that region of the image. So the color lookup table, so this itself this thing here is called the color map. It's also called a color lookup table. Oops. Um, so lookup table. Sorry for the slow speed on this. I've not got my pen um, with me, pen tablet. Okay, so it's a color lookup table. There we go. Oops. LE. Okay, so it's a color lookup table. Let's just tidy this up a bit. That's horribly messy. Okay, so you can hopefully just about read that. Okay, so the way that this works is that within so let's drop some numbers in here. So let's say we've got color number 1, color number 2, color number 3, color number 4, and so on. And so if we're using, if we, well, let's come back to this point. So let's say we have capital I number of values in this color lookup table. then we can only display simultaneously large I possible values in this image. And how does this work? So what we have within the this two-dimensional array is effectively let's say a number like 5, number 2, a number 3, a number 1. And the way that the color appears on screen is that and this image, by the way, is now called a paletted image, or sometimes a color map image. But paletted is it kind of conveys the notion of paint by numbers, and so this term is in quite common use. So this is a paletted image, and um, so to represent um, when the image is displayed, each of these numbers is used as an index into a row of the color table or the color map. And so, for example, the color number 2 might specify a red intensity of, let's say, 0.1, green intensity of 0.1, and a blue intensity of 0.3. This is going to be a sort of bluish, a faint bluish color. So it's sort of like a gray blue. The gray comes from 0.1, 0.1, 0.1, and then there's there's 0.2 of blue added into that. So you're going to have a sort of grayish blue color, right? So color 5 might be something else. So color 5, I'm not written that in here. So we've got, let's say, 5 here, and then a few more rows in here. Okay, so color 5 might be something that it might be pure black, which would be 0 on red, 0 on green, 0 on blue. So the point I'm making here is that a paletted image might conceivably have colors scattered, or, sort of all over the place. So that bigger numbers in the bigger numbers in the image array don't necessarily map to brighter values on screen. Because the only way you can interpret a paletted image is through using the palette, is using the image, looking at the image and mapping it through the palette. So you need to look at the explicit RGB values of each of the colors in inverted commas that are present within this image. And the only way you can interpret how this image is going to be displayed is by mapping it through the palette. So paletted images are quite widely used in image processing. They are particularly found on devices that either produce very large images, and so you want to be as efficient as possible in storing the image. So, for example, in this case, rather than storing red, green, and blue values explicitly at every point in space, we store the color at every point in space. So we only need one value rather than three. Now that may sound like a very low amount of saving, and that is true, but paletted images are very heavily used within medical imaging. So it's something that you need to be familiar with in how a palette works. I think there's another general point here, which is that often you can't really necessarily guarantee that you can interpret the values in an image and how they map to intensities unless you have access to the palette, or you're explicitly told what the palette is that should be used to display the image. So that's a really key point. And as I say, in the practical, you're going to go into looking at paletted images in some detail. Okay, now so a paletted image is a special type of image representation, but it is quite consistent with what we've been talking about before, in which we have a single value at each point in space. and that's, piloted image is exactly like that, except that that single value is not treated directly as an intensity, but rather indirectly as an intensity through the the color map. And so a single piloted image, or a piloted image which has one value per pixel, can be used to represent a color image. However, if we want to represent a color image, there's another way to do it, which is to have three separate arrays. So one array to represent red, one array to represent green, and a third array to represent blue, or the blue intensity channel. Okay, and so that would mean that rather than having a single array, you've got three arrays. And so the way you can represent this is to talk about, let's say, fr as a function of m and n. Yeah, fb as a function of m and n. And uh, well, I should have dropped fg in there. So fg is a function of m and n. And let's use capitals here for consistency. So red, green, and blue. There we go. So all three as functions of m and n. So three arrays. Notationally, you might also think of this as one three-dimensional array, but the third dimension will be an index over color space. So what you can find is f as a function of m and n, and c, if you wish, where c represents your color channel, and whilst m and n can take values over little m going from 0 up to the number of rows minus 1, little n going from 0 up to a number of columns minus 1. C will only take values of 0, 1, and 2. Or if you like, 1, 2, and 3. But that would be a natural way to represent this three-dimensional array of color values. Okay, so that gives us an introduction to piloted images. So just to wrap this up, the 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 use of a color map or a color palette does save a little bit on the storage requirements over a full RGB image, which, by the way, is what I should have explained over here. So let's just jump to that. So this thing here is sometimes described as so this one here is sometimes described as an RGB image because you explicitly store the three values of red, green, and blue at each pixel location, and so you need to have an explicit red array, an explicit green array, and an explicit blue array, or a three-dimensional array, sometimes called an RGB array. In contrast, when we talk about a piloted image, we may get away with, or we do get away, I would say, with storing one value per pixel and then also having an associated color map so that that value is mapped through the color map to tell you how that pixel is displayed on screen. So as I've explained, we've used a convention which is to label the rows going from 0 up to n minus 1, columns from 0 up to n minus 1. But there's something else that we need to point out, which is that the way that that things are organized here is that m, the row number, increases that way, and the column number increases that way. Okay, and this is f as a function of m and n. But let's contrast this now with what we looked at before, with f as a function of x and y, which is our more familiar Cartesian coordinate system. Okay, so the first thing to note here is that, and this is always a point of confusion when you start getting into practical image processing and trying to compare it to what you're familiar with in an XY setting. And it also becomes a practical problem because plotting commands in something like matplotlib will tend to natively use an XY convention, whereas the image display routines, even within matplotlib, use this convention. And here's the catch. So here, X refers to that direction going left to right. Okay. Whereas going left to right here, or going left to right here, is the second coordinate of this representation. So that thing there kind of is associated with that thing there. And this coordinate here, the row coordinate here, is associated with the y coordinate over here, because x is that way, right, left to right, and that's what the role of the column coordinate is, and that's the second index of this. Whereas y, which is the going up and down bit, is handled by m, the first coordinate of this representation. So this is where we have a clash of cultures, if you like, between Cartesian coordinates and this this notation, which comes from matrix notation. So we don't usually think of an image as being a matrix. We think of it as being a two-dimensional array, but we use this this sort of row column kind of indexing arrangement. So this swap around does cause some confusion when you get into the practicals. So just be be aware of this. But there's a second catch here, which is that the y coordinate, so positive values of y generally go in that direction, okay? And the catch is that positive values, so this is plus VE, let's put it here, plus VE, so positive direction is going up, okay? Whereas for, sorry, just ignore that dash there. Whereas for in row indexing, positive values go in this direction. Okay, and so negative row values will go upwards, which is the opposite of negative row values here, which go that way. Or negative y coordinates, which go that way. So just be aware of that. You can look at it and it's pretty obvious, but you get into the lab and you'll find it's going to be a headache to figure out. But it's manageable. Okay, so I talked about the having 1 byte for each of red, green, and blue as a fairly standard thing on digital cameras. So mobile phone cameras, DLSRs, etc. They will often capture to 8-bit precision on red, green, and blue channels. On medical imaging systems, so most X-ray CT and magnetic resonance imaging or MRI scanners can produce images which have between 12 to 16 bits of intensity precision per pixel. And even and that's and so what you get coming out of these scanners is for for grayscale images, you will have more bits than you will generally produce in a grayscale images that has been obtained from a standard digital camera on a mobile phone. And there's a bit of a mismatch because most of our displays, and this is partly due to limitations both of display technology and also simultaneous or human perception of what's called simultaneous contrast. So how much dynamic range of intensity or what precision you can perceive uh, in in intensity differences in normal viewing conditions is fairly restricted in the in humans. So most displays will only allow between 8 to 10 bits of intensity resolution. And that means the number of distinct intensities that the monitor will be able to display is somewhere between 200, but it's actually slightly lower than 256. 8 bits corresponds to 256, but it's somewhere around 200, so it's between 7 and 8 bits. Um, and 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 tops out at about 1000, so 1000 different intensity levels, so that's about 10 bits. That's the absolute maximum under the best viewing conditions. So we have a mismatch because we have lots of bits of intensity coming out of or precision coming out of the measurement system for X-ray, CT, or MRI, but we have an inability to display all of that information on our standard computer monitors. So there is a technique that is in very common use in medical imaging devices to be able to handle that. And it's known as grayscale windowing. Okay, so to understand grayscale windowing, let's jump back to our board scene and let's do a little sketch of this grayscale windowing thing. So we have a measurement system that is capturing, let's call it a measure. Let's just draw a sketch here. So this is to some extent conceptual, but let's say that we have some sort of measurement. And that measurement has a lowest possible value that can be measured or represented within the system. So beneath this level, we can't distinguish zero, no signal from this smallest sample. So below here, we just are doing silly things. We can't measure anything. But then we have a maximum as well, maximum possible value that our system is capable of measuring. So this is the range of measurements we can capture. So if you want to think about an analogy of this, this range here is capturing something like if you have a ruler and you've got the length of the ruler, the maximum length of the ruler, let's say it's a 30 centimeter ruler. So that's your 30 centimeter point. It's the biggest thing you can measure, the longest thing you can measure with the ruler. Okay. The smallest thing you can measure with the ruler will correspond to that the very the gap between the starting point on the ruler and the very first division you have, very tiny division you have on the ruler. So you know that rulers have the big divisions and they've got the smaller divisions or the smaller the small little increments between along 1 centimeter, which corresponds to 1 millimeter. So this would be the 1 millimeter point, and that's your. This is sometimes from here to here. We sometimes refer to that as the dynamic range of your system, which is the range between the smallest thing you can measure and the biggest thing you can measure. This is called DR, which stands for dynamic range. Which is a fairly obvious term once you think about what it means. Okay, so we've got a certain dynamic range of measurements that some kind of imaging system can capture. This dynamic range. We've got some kind of minimum value we can measure and some maximum value we can measure. So the way that we can quantify this dynamic range is in terms of bits. So there's a very formal way to do that, but if we think back to take this very simplistically, if and in a way that's very consistent with the course and with the module and with the practicals, you're going to see that in the practicals you're often going to deal with 8 bits of precision in a measurement, and that corresponds to a dynamic range that where this value here will correspond to 0, and that value up there will correspond to, let's say, 255. Okay, so that gives you a dynamic range that corresponds to 1 byte or 8 bits of value. But in our measurement system, what we're saying is we can actually have many more possible values. So if we have 12 bits of dynamic range, then that means that this value here is going to be 2 to the power of 12, okay, minus 1. Okay, so 2 to the power of 8 is 256, 2 to the power of 9 is 512, 2 to the power of 10 is 1024, 2 to the power of 11 will be 2048, and 2 to the power of that famous game, and 2 to the power of 12 will be 496. So this is going to be 4095. Okay, so that's the sort of value that can come out of some scanners. So a 12-bit measurement will produce values between 0 and 204, 495 as a number, as an integer measurement. But what we're saying is that our display, if we display this as a grayscale image, then typically, in order to display that sensibly, so this is our display device, this thing only has 8 bits of dynamic range. So this is our display. So by display device, I mean, basically a computer screen, okay? Okay, so this only has, let's just put device in there. Okay, so that range there is only going to be uh, 8 bits. Okay, so I hope that's clear because that's an 8. Great. Okay, so this is so this range here is 12 bits, and that's 8 bits. So how are we going to squeeze this 12 bits into those 8 bits? So that's where the display windowing comes in. So the first thing you can do is you can just scale things down to fit 8 bits. So you can just, if that's 495 and this range here is 0 to 255, you can simply divide 495 by 255, and that gives you a scale factor that is applied to intensity that will scale values in this range down to fit values in that range. So if we were to depict what that looks like, it basically is doing something like this. So you basically draw a dash. Oops. Oh, that's a pretty messy looking dash, series of dashes. So let's make that a bit nicer. And let's use a different color to make this clearer. Or in fact, I can be quite clever here and switch using a different color and also draw using this to make my life a lot easier. So here is our a representation of that scaling. Oops. Try that again. So that gets mapped to that, and that value gets mapped to the smallest value there. So that's a scaling where the full range of this gets mapped down to the full range of that. Okay, so that's one way that the windowing can be done. But we can also do the windowing in a different way. So we can also do it like this. So I can arrange a window which has a width equal to that. So something like this. And then what I can do is I can slide this end of this windowing region here in intensity space up and down so that I'm losing part of the intensity space. So basically anything below this point here in intensity in the measurement will still get mapped to the lowest intensity here, and everything above this intensity in the measurement space gets squashed down to match this intensity, the highest intensity. And in this arrangement, everything between here and here gets mapped to a value between here and here. So a direct mapping, if you like, without any scaling. But I can also arrange things so that these ends, as I say, can slide up and down this intensity range. Okay, so let me just illustrate what that looks like for clarity. So interestingly, my pointer here is not working. Oh wait, or is it? No, it's not. Okay, the object, oh wait, the object pointer isn't working for some reason. Okay, so let's do this the hard way. So just get rid of those two. And let's redraw those two, but this time using a different arrangement. So we're going to keep the width between those two lines the same, but instead we draw it like this. So we have this gets mapped to the highest value, and then this sort of same distance here, I'm going to move from here down by that distance. So this is 1, 2, 3, 4, 5 units. So I move down 1, 2, 3, 4, 5 units. And from here, I then go like this. Okay, so this is a different type of mapping, but it's done by taking that window level, which has the same width as the output display device, and shifting the top end and the bottom end upwards. But I can do that, I can sort of swivel this back and forth to any range of 8 bits, but sort of with a starting point and an ending point that can be moved up and down. So the way that this is done practically is, well, practically, I mean, kind of, if you walk into a scanner room where somebody is looking at a medical image and they're using the windowing to display these 12 bits of information on, or to map these 12 bits of information onto your display device, they're basically, they've got different ways that they can do this. They can So in one setting, you basically play with a mouse-like device, and that mouse-like device, while you're fiddling with it, it's expanding and contracting this range here. And if you switch it into a different mode, it's shifting this uh, this this gap here, so in between this point and this point. So if I fix the width of this, but I grab hold of that central location and shift it up and down, then I'm basically capturing different ranges of the measurement space and splatting them onto the display device. And practically, that's what people will do very quickly. So trained radiographers are very good at very quickly figuring out how to both change the width of this and also the central location of the input to this mapping onto that display device. And it's done interactively because, of course, a priori, right, you don't know exactly where in intensity space you need to look to see something to sort of exacerbate what gives you the diagnostic information that's relevant. So you have the ability to very rapidly move play around with this mapping between the measurement space and the display device representation space, if you like, in order to be able to maximize your capacity to interpret the image. Now, in the practicals, we're going to play a little bit around with manipulating this mapping, but I want you to be aware of it and how it's used in a diagnostic context. So it takes a bit of getting used to because it's not something you meet in, let's say, everyday life. The closest thing you will have met is if you've used an oscilloscope in, let's say, a practical session in an electronics lab. So perhaps those of you who've done that will, if you think back to that sort of exercise, then what you're doing as you fiddle with the knobs of the oscilloscope is changing the scaling sometimes on the y-axis, and that's what you're doing here. You're scaling the gap between the lowest and the biggest value, and then as you change the bias on the oscilloscope, you're moving the central bit up and down. So that's the analogy that perhaps you might have met yourself in other courses. Okay, so that deals um, with this thing about intensity representations and grayscale windowing. So I was a little bit excessive, but it's good that you meet it somewhere before you get into the practicals. All right, so now we're going to talk about the perhaps the most boring thing you can imagine, which is image storage formats. But you need to have a little bit of familiarity with this. So you will probably have come across things like TIFF images, JPEG images, PNG images in the past, and I don't think anyone hasn't met these sorts of things. And there are lots and lots of different formats. When I last looked this up, and this I have to admit, this is probably about 20 years ago, I came across around 50 different file formats in reasonably common use. So what's all this about? So uh, so there is this term called serialization, which is a term that I hate, but it's one that is in very common use in computing and in computer science. So when we talked about an image as being a two-dimensional array, which is then is effectively is mapped or displayed through a display device computer screen. But on disk or in digital communication, that two-dimensional structure is effectively broken. It's what's called serialized. And what that means is that an image is just a stream of bytes that is either sent over a network or stored on disk or in some sort of some sort of electronic storage. Um, we've already seen that there are different ways in which these bytes can represent the colors of an image. So first of all, we can either have an RGB image where we explicitly specify each of the red, green, and blue values for the image, Or we can have a color map or paletted image where the image is represented by an array, and the values in that array must be mapped through a color map or palette structure in order to figure out what color appears on screen. So, so there are different ways in which that image can be represented in the stream of bytes or mapped to that stream of bytes. And more concretely, what we need to do is to know how that stream of bytes should be reconstructed into an image. So, first of all, the most obvious thing we need to figure out is um, if we've got a stream of bytes, how do we put those into a two-dimensional array? And what that means is the first thing we need to figure out is what is the size of the array that the image should be it should be used to hold the image. So a stream of bytes on disk, just sitting there, very difficult to interpret how to put that into an image. You need to say, okay, this stream of bytes needs to be packed into an M by N sized array in memory. And that's the first piece of information that you need to have. Number of rows and number of columns. Second thing you need to know is the color space, how the image is represented. Is it a paletted image? Do I have just one image array? Do I have three image arrays? So that stream of bytes on disk you need to have accompanying information that tells you how to do all the other stuff. So that is the role of a file header. So when we store an image on disk, the 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 really important information that's sometimes referred to as meta information is stored in the image file header. And the different image file formats effectively just have different ways of storing that meta information associated with the image. And that meta information is normally stored at the start of a file on disk, or if you're transmitting an image over a network, the first few bytes or few hundred bytes will convey that sort of information at the person who is receiving, or the device that's receiving the the stream of bytes. So the headers tell us about the dimensions of the image, so the number of rows and the number of columns, or sometimes width by height. The color representation that's used, whether a color map is used or not, and if so, if a color map is being used, then the palette or the color map also needs to be stored in the image file. There are different palettes that could conceivably be used, so for example, you can have a monochromatic palette in which you only got shades of gray. You can have a color palette which has a subset of all possible displayable colors, but that also needs to be stored with the image on disk. So the headers vary from one file format to another. So PNG headers are different to TIFF headers, for example. And so that's the main difference between all these different file formats. It's the mechanism or the way in which that header or meta information is stored. Now, medical images have a very specific format that is indicated, which is known as the DICOM 3 standard. So DICOM stands for Digital Image Communications in Medicine. It's a really super comprehensive standard for writing and transmitting medical image data. You can imagine that for medical image data, you need to be absolutely precise about pretty much everything that has gone into creating the image. And that's why there's a standard for it. And DICOM is the standard that is still in widest use. Now, let's have a quick look at what this DICOM stuff looks like. Um, so I'm just going to open a web browser and find you a little bit on DICOM. So I'm just going to get this prepped and open it for you. So uh, just bear with me 1 second. Okay, so um, my screen has gone blank for some reason. Just bear with me for 1 second while I get this up and running. Uh, well, why has that gone blank? Just here we are. Okay, right. So good. So let's jump to yeah, good. So hopefully you can see that now. Let me just shift this over properly into our window. Okay. Yeah, I'm possibly not capturing everything, but oh yeah, darn right I'm not. Okay, that's better. So um, the DICOM file format. Let's just look up DICOM, and we should get nice. Oh, I see. Okay, my internet is dropped, so it's probably not helping matters. Great, this is where I wanted to get to. Okay, so the DICOM library is this is not the official DICOM site, but it shows what this meter information consists of in the DICOM header. So there's a whole bunch of very formally specified things. This stands for service object pair, if I'm not mistaken. But it's a very it's a very detailed format. And what you're seeing here is the possible information that's stored within the header. Now, the things that begin to be recognizable are stuff like this: referring physician's name, referring physician's address. So these are pieces of information that are necessary to be stored alongside a medical image, because you need to be able to get the medical image back to the person who's going to do the diagnosis. Modality here refers to, for example, do we have an MR scan, a CT scan, ultrasound scan? There is actually a special series type for nuclear medicine. You've got information about the study date. So what date has this image been acquired? And within a study, you can have a study. You can also have a series of scans that are taken at different points in time, and you can also have an acquisition date for an individual scan. So there's a huge amount of um, flexibility, but ironically rigidity in this specification. But DICOM files are vital to storing patient information. So date of birth, sorry, patient's date of birth. There's even patient's date of birth in an alternative calendar. Uh, patient's alternative calendar, interesting. Um, and patient's age, size, weight, etc. So huge amount of meta information. DICOM images tend to be huge, and a lot of that is the header information. But there are lots of nice tools that allow you to read the DICOM files from disk and to then convert them into TIFF or PNG or whatever, but more importantly, to read them from disk and also interpret this meta information that is stored in the file header. So within the practical, we're going to be also looking at DICOM, and so you'll be getting some familiarity with what DICOM images look like. Okay, so let's now. So I'm going to take a pause there, and we're going to come back and talk about simple mathematical models that we can use to get our heads around the image as an array or as a collection of values that have been measured over two-dimensional space. So we're going to introduce the minimum number of simple mathematical models we can use to describe images, which we are also going to relate to other things that you've met in the past, I hope, such as linear regression. And we're going to also talk about statistical models of images in the most general way possible.